let's get started, guys. Before I forget, because I will tell you tomorrow as well, I hope, but just in case I don't, I have a meeting on Friday during our time. And I'm pretty sure half-hour meetings never end up being half-hour, so I know I won't make it back. So we're going to be finished tomorrow, green theorem, which is fine. We're not going to be overshooting the time. It's not like you'll be in any great rush. But just to remind you, there won't be a class on Friday. I'll be at a PCE meeting. Okay, let's get started. Here is Green's theorem, which says if you want to find a line integral, you can find this double integral instead. And dA will be dx dy if the shape is a rectangle or rectangular or triangle. And you would probably change it into polar if it's something to do with a bit of a circle. And let's get started. I'm picking my usual just variations on a theme. So, here is the first one. Just got a couple set up to get us going. Here is a really ugly line integral. And the boundary, the line is, it has to be a loop, right? C is a loop, right? You know, you go and you come back and whatever. And its boundary is by these two curves. And so we are going to find what this line integral is. If I had to do this the usual way, this would be horrendous, right? If I had to do it parametric, you know, last week's stuff, you really, really do not want to do this one. So in this case, this is P and this guy is Q. So I know that my line integral, I'll just call it that, is going to be equal to our double integral over a region D. And the guys that we have are the partial derivative with respect to x, take the partial derivative with respect to y, dA. In this case, it's going to be a double integral D. If you differentiate this horrible mess, but if you differentiate it with respect to x, all you get is 8. Take away. And if you differentiate this guy and you do it with respect to y, all you get is 3. Would you agree that this ugly thing just turns into 5? I mean, how nice can nice be? Would you agree, even if it was only for this one question, isn't Green's theorem a godsend for work? Right? It's an efficient way of getting the answer. Now I have to focus a little bit on the boundary fella. And if you do y equals x squared, well, I'm going to call that the square root of x. And then if you do y equals x squared, it's going to look like that. And we are talking about this is the region D. I don't know, and I'm now having second thoughts about this. I don't know if they mention orientation. Oh, great. It's positive direction. So if you didn't know, it would be going up this way and down that way, right? Anti-clockwise. So how would I define this? Well, we're going to be doing an awful lot of double integrals, which means we're going to have to bring back a lot of things that we've not done for a while. If I was doing this guy, would you agree it'd probably be best to do it vertical rectangles, right? Little strips. And that point there is pretty easy to calculate. So I would be doing x is going from 0 to 1. And y's would be going from the top guy, square root of x. Top guy, yeah, square root of x. Bottom guy is x squared. So you're happy about x squared on the bottom to square root of x on the top. Are we good with that? So that's basically region D described. So I'll return back now to our integral. And it's going to be the integral from x equals 0 to x equals 1, because you need numbers here. And it's going to be from y equals, who's the little guy, x squared to y equals the square root of x. And this is just 5. And then I'll do a dy and I'll do a dx. I think that's where I want to stop. Would you agree that you can't separate this integral because the limits of integration here have x's in it, right? So you're going to have to do the y's first, right? And then do the x's next. Are we good with me just dotting that and saying you could finish that your own? Right. And so that's the first one. Still cool. I mean, before I leave, just look at how ugly that is. And look at how nice that is. They don't expect that kind of benefit. But one of the reasons Green's theorem exists is because it's to make your life easier when you want to find a line integral, right? Some line integrals, if you just do them, you know, the parametric, you know, the RT and all that stuff, just grow into some ridiculously ugly integral. And if you do it as a double integral, it's a very simple one.
Please tell me Green won awards for this.
This one, I should check it. But Green's theorem works because you don't need to be conservative, Terence. That's another advantage of it. So this here doesn't need to be, you know, this guy doesn't need to be equal to that guy. In fact, it's not, it's 5. If it was equal, in other words, if I had a conservative field, wouldn't this always be 0? And the answer would be 0. But that's true, isn't it? If you're a conservative field and you do a line integral that starts and finishes at the same point, aren't you guaranteed to get 0 as the answer every time? Did that answer your question, Terence?
I got the whole thing about the conservative fields. I was being a little facetious and wondering if Green had won any accolades for his theorem.
He actually did. The accolade that you get in math is very often not money. You just get something named after yourself. In fact, I think the convention is that someone else has to name it for you. So you can't say, I'm calling this Green's theorem, because people would think that would be pretentious. So what you get to do is you get to do it and people say, that's a great theorem. Who did it? Oh, the guy Green done it. Okay, we'll call it Green's theorem. That's probably how it works. Okay, here's our next fella. This is our guy. This is the fella that we're going to be doing our integral form. Our line integral is essentially that guy. And it's double integral over D. Is this fella. I keep having to look to make sure I don't get the x's and y's jumbled up. Now, in the way that this function is written, this entire piece here, up to the comma, is P. And then this piece here, that's the Q. So my line integral is going to be a double integral. If you differentiate this expression here with respect to x, that is a downright ugly question. Well, evidently it must be here for a reason. Okay, if you differentiate with respect to x, you get a y. And here you get a cosine x, take away an x sine x. It's pretty messy, that's that bit. We'll bracket around it. Take away, if you differentiate this fella with respect to y, you get a cosine x and a negative x sine x dA. And oh, kill. Okay, I take it back. Would you agree that's a very nice double integral? I didn't think it was going to be a very nice one, but it ended up being very nice. Now we have to figure out who our D is. It's a triangle, I believe. So you start off at the origin, then you go to 0, 8, which is up here. And then you go 2, 0, I know it's not to scale, which is here. And then finally, you return back to the origin. And I have noticed something that's quite important. What orientation is this curve?
Is it negative orientation?
It is. So don't I have to stick a negative in front of my double integral to compensate for the orientation? Remember that? Green's theorem's plus if you're going anti-clockwise, right? And that's called a negative orientation. Now, I want to know what that line is. I keep screwing this guy up, but here it's y. I know it crosses at 8, and I believe its slope is -4. Do a double check for me. Does that look good? Y equals -4x because of the slope, plus 8 because of the y-intercept. Okay. So I'm going to go for the rectangle. I'm going to go vertical and scan from left to right, which means that the x's are going to go from 0 to 2, and the y's are going to go from 0 to -4x add 8. Are we cool with that? Right. So switch places. We should be ready to put this package together. It's a negative of x going from 0 to 2 of y equals 0 to -4x add 8 of a y, a dy, and a dx. Okay, I think I'm good to go here. Would you agree that's just pretty standard double integral? You can't separate it.
You can't because of the equation.
Say that again. I didn't catch it, Sally.
Said you can't separate it because of the equation.
Yeah, because if the limits of integration contain a variable, don't separate it. If they're numbers, you could well separate it in a lot of situations. And yesterday, I think we got a couple where they separated, didn't we? But not today. Right? I'm not saying that we won't get one today, but there's less chance. Let's just scan through, find somebody. No way in the world am I picking random functions. Did you see that last one? It looked horrible, but it ended up being y. That's because people much cleverer than I am create questions where that happens. If I just randomly pick a p and a q, we'll probably end up with a double integral that's worse looking rather than better looking. So next fella is 5. And we're doing a line integral written in that format. The function f is going to be e to the -x plus a y squared and e to the -y plus an x squared. Interesting. And the curve C consists of the function y equals cosine x, starting at that value and then finishing at that value, and then a line pi upon 2, 0 to -pi upon 2, 0. So I'll put a little bubble around that. It's quite messy looking curve. I'll start it off. The line integral is going to be the double integral of dq by dx, take away dp, dy, dx. And this guy's p, this guy's q. If you differentiate this with respect to x, you just get 2x. And if you differentiate this with respect to y, you get 2y. That's a very nice option. I'll just call it dA for the time being. And now we'll focus on this guy. If you do the cosine function from -pi upon 2 to +pi upon 2, and then you join it with the dot, let's see what the orientation looks like. You're going from this point to that point, and then you're going from that point to here. Do you see the orientation again? Positive or negative?
Negative.
Right, so remember to stick the negative on your answer. That's the only difference, right? Which, yeah, so just be careful, because if the answer's, if you do 42 and it doesn't like it, well, you try negative 42 before you do anything else, just in case it's a simple, you forgot to incorporate the orientation. This curve here is pretty straightforward. It's y equals cosine x. So if I wanted to describe this region, I would say choose an x from pi upon 2 to negative pi upon 2. And why? Well, pick a rectangle, a vertical one. And what that tells me is that on the small side, we go 0, and the top side, we do cosine x. Are you comfortable about the limits of integration for d? From negative pi upon 2 to pi upon 2, and from 0 to the curve. So back to here. It's going to be negative the integral from x equals negative pi upon 2 to pi upon 2, from y equals 0 to y equals cosine x, and the function is 2x, take away 2y, dy, dx. But I want to take this one a little bit further. If you integrate this expression with respect to y, you will get 2xy, take away y squared, evaluated at y equals 0 to y equals cosine x, dx. We happy with that? Integrate 2x, you get 2xy. Integrate minus 2y, you get y squared. That now becomes, right, if you plug in cosine, you're going to get 2x cosine x, take away cos squared x, minus a whole load of nothings. So that's what we get. And the reason I wanted to take this fella a little bit further is I'm going to have to integrate this guy, and I'm also going to have to integrate this guy. You probably should do them separately, right? Because they don't really, they don't play well together. What method will I use to integrate 2x cosine x?
That would be an integration by parts, wouldn't it?
Yes. And how will I integrate negative cos squared x?
I used 1/2 plus cosine of 2x over the whole thing, and then that divided by 2.
Right, so 1/2, 1 plus cosine of 2x, right? You do a trig identity, and those guys come out, and you are done. Any questions so far? Does Green's theorem have a kind of flow to it? You change a single into a double, you change the loop into an area D, and then you basically, it becomes a double integral question, which hopefully we've had plenty of practice on. Oh, this one is good. I remember seeing this question earlier when I was looking at what I was going to do, and this one is just weird and cool. I'm going to write down the way it's written in the website. It's using that I-join notation, which I dislike. So I'm now going to rewrite it. how I would write it. And they go here and say, use a method, or using the method of this example, and you click on the example and it goes and shows you an example, which may or may not help you. And it tells us that C is positive orientated and that it is enclosed, a simple closed curve. But no mention of what the curve is. Right? It could be a circle, right? Could be an ellipse, could be a triangle, right? All I know is that simple close. Oh, and they mention it goes around the origin, which actually doesn't really matter. And we got this guy. So I'm going to call this guy P, and I'm going to call this guy Q. I'm not going to do the details, but I will get again at the start. It's going to be a double integral of a region D, and it's going to be dq by dx, take away dp, dy, dA. So who shall I pick? Let's pick just this one. If you want to differentiate this ugly fraction, partial derivative with respect to y, I'm going to have to do an f dash g, take away an f of g dashed all over g squared. And that's going to get me, well, if you differentiate the top, you're going to get 2x, and you're going to leave that guy alone. Take away, leave this guy alone, and then you're going to differentiate the bottom with respect to y, which is 2 lots of x squared plus y squared to the power of 1 times another 2y. And the whole thing ends up with the bottom squared, which now is 4. And this guy is 2x, this guy is x squared plus y squared squared. This guy is negative 4x, no it's not, it's actually more than that. It's negative 8x, y, x squared plus y squared all over x squared plus y squared to the power of 4. And you would quite naturally, because that's what I thought when I had a try at it, you're going to look at that and say, that's not what these guys are meant to look like. Aren't these guys meant to be 8 or 4y? Not a horrendous guy. I'm not going to do the dq by dx one, but I can tell you what's going to happen. Anybody, any guesses why this question was actually a trick question?
dp dy is going to equal dq dx, and it's going to be conservative field, so the answer will be 0.
Yeah. It ends up being a conservative field. And if it's a closed loop and it's a conservative field. So the trick here was to just keep going and then go, oh, bugger it, the thing's 0. Well, great. That means it's a conservative field, which means that the integral of 0 is 0. And great, it doesn't matter what curve you pick. And it doesn't even be around the origin. Couldn't the curve be anywhere? Conservative field doesn't care. So, question 6, very easy answer. Pain in the butt to do from scratch. Right, there's now a bunch of questions, and they start at number 7. And I'll do a quick search to tell you where they go. 8 does it. 10 does it.
Was there a trick that you knew to know that, or did you just have the answer?
No. After I'd done the first one, I just looked at their solution and said, oh, bugger, I didn't need to do it. The second one's the same as the first. So
Okay.
no, there wasn't a trick. You just did it and then you found out. Okay, so there's 3 questions, 7, 8, and 10. And these guys are not trick questions, right? They really are Green's theorem, right? You really do get a number that's not 0 when you're finished. But they do something a little bit differently. They ask you to do two distinct questions. They ask you to find a line integral, and they ask you to evaluate it directly. And then they ask you to evaluate it using Green's theorem. And they're getting you to do that. I'm assuming that they're getting you to do that just to convince you that Green's theorem actually does work, right? Because right now we've been doing them, haven't we? And saying, hey, this guy Green figured out it works. Trust him, he's a mathematician. Here is my advice to you. Do Green's theorem first. And if you want to, pick a question and do it the long way, just to convince yourself. And if you're one of those doubting Thomases, do it for every single one of them until you're finally convinced that Green's theorem works. And if you're one of those people who just believes me because I tell you it works, you might choose not to evaluate any of them. Because do you know, if you want to do these directly, can you trust me, you're going to be spending 20 minutes, 30 minutes doing it? Because that's the ugly way, isn't it? And this is going to be the nice way. But that's your choice. So I have no problems that if this is 16 pi, you're going to call that 16 pi because you know it's the same thing, right? But you want to convince yourself, go for it. So let's pick one of them. It really doesn't matter which one, does it? Well, that's a rectangle. Oh, that's good. I like this one. Okay, I'm picking question 7. So I'm only going to do 7 out of that set of 3. And let's get started. It's got that funny little circle around it, which I remember mentioning yesterday. And they mention C, of course. And C is counterclockwise around the circle, origin radius 3, right? So you're basically C is that guy, right? I'm sure, didn't I tell you that notation is just a line integral that's a closed loop, a simple closed loop, right? Couldn't have just written that down. Won't it mean the same thing, right? So it's a notation. It's a bit like somebody saying f dashed of x, and then somebody saying y dashed, and then somebody else saying dy by dx, and they all the same thing. They're all different notations for derivatives. So don't freak out over that. Not that you would. All right, I'm going to call him P. I'm going to call him Q. So this guy better be nice. I'm 99% sure he is. If you take this with x and subtract this with y, differentiate this, you get 1. Differentiate this, you get -1. There, let's double check. 1, -1. 1, take away -1. Okay. So that's pretty good. Would you agree? 2 is a really nice answer. So if you did it the other way, it probably will take you 20 minutes, but not this time. I have positive orientation, right, which means it's going the right way. Circle, radius 3. Would you agree that this guy here would probably work really well if you just turned it into, say, polar, because it is a circle?
Yeah, and so it would be R goes from 0 to 3, and the pi would be from 0, and the theta will be 0 to 2 pi.
And so, no particular reason, theta equals 0 to theta equals 2 pi, r equals 0 to r equals 3, and now I'm about to do a deliberate mistake. What did I miss?
R.
You are.
Yeah. Isn't it dead easy if you're in a rush to drop something like that if you're not careful? It makes a big difference, the answer, so you've got to be careful. Is this one separable?
You get 2 pi, the integral from 0 to 2 pi of 1d theta. And then you multiply it by the integral from 0 to 3 of 2r.
Okay, that one gets you 2 pi. This one gets you r squared, which what gets you 9. Answer is 18 pi. And I'm on a roll, it's 18 pi. That question is like almost designed for Green's theorem, isn't it? It was so nice when you turned it into a double integral. And I'm pretty sure it'd be so much more ugly if you tried to do it any other way. Any questions so far? I'm getting a vibe that this is moving pretty smoothly. Right?
What's the meaning of life?
42. Hitchhiker's Guide to the Galaxy. Let's look at 9 then. Kind of odd one out. In question 9, we're back to a line integral. It's an XY question.
No, I was just gonna say, well, if the old answer to life, the universe, and everything is 42, then what's the ultimate question to life?
That's correct. What is the ultimate question? And if you watch the series, you'll find out what was going on there, because I'm not going to be a spoiler. Although I have to, now that I'm doing this, I have to share with you one of my nephews. He's more like a brother. My sister got, when she married, as we say in Scotland, a knee user. Right. I'm sure Americans have probably got better phrases for him. Anyway, they get divorced pretty.
Did you say a May user?
No, a knee user. Scottish. Nay means no, and user means use. So he's somebody who's no use to anybody, right? He was not a good husband, didn't like him. My dad hated him before they got married. He hated him while they were married, and he hated them after they got divorced. So he never got a chance with my dad. He was good at picking people and figuring out what they were like. My sister, on the other hand, thought because he was a big hunk that somehow that made him a good person, which
A schmuck.
It made him a schmuck, yes, not a big hunk. Anyway, back to the story. Hugh, because my sister was divorced, we took in Hugh, and Hugh, I was about 8, and he was just like a baby. He got brought up for the first 10 years of his life until my sister got married again, and then we took over. So we kind of looked after him. He was my brother. Anyway, back to the story. He had a really annoying habit of doing spoilers. So if you didn't see Star Wars or whatever it was, and he had seen the movie and he knew you were going to watch it the next day, he would come in and he would start off, "Oh, it's a really good movie." And you say, "Okay." And then I'd say, "I don't want to know anything." And he'd say, "You wouldn't think that Darth Vader was so-and-so's father, would you?" And he would put a spoiler right on you. And I don't know if he did it deliberately, or he just got so excited that he didn't, that internal voice, external voice, he didn't have much control over it. But the number of movies that guy has spoilt for me is not true. So if there was a movie going out, you just made sure that you watched it before he did. I was never, although I thought about it, I was never the person who would say, "Hey, Huey, if you haven't seen this sci-fi movie," and you say, "Yeah, you wouldn't believe that so-and-so get killed at the end, would you?" Just to spoil it for him. But I'm not like that. Although I do think about nasty things like that sometimes. You get anybody in your family that's like that? That just spoils things because they can't help themselves? No? Okay. My family's always weird. Okay, let's do a double integral of this, fellas. Hopefully it's just getting routine now. Okay, your P, your Q, and P is going to be, what on earth is P going to be? This one first anyway. with respect to y, 3x squared. And with respect to x, y squared. Okay, I can handle that. Okay, this fella here is a triangle. You're going 0, 0, 2, 2, and then 2 along, 4 up. 2, 4. And the order was there, there, there. Okay, so it's positive orientated, agreed? This guy, I've seen worse. So it's 3x squared, take away y squared. I would do, because I like it this order, I would do vertical rectangles. And x would go from 0 to 2. Now, if we're talking about the y values, don't we need to know the equation of that bottom line, and we need to know the equation of this top line, don't we? Right. So that bottom line passes through the origin into 2, so I believe that is y equals x, and that belongs on the bottom. And this one here is also a straight line going through the origin. What's this? 4 by 2, so that's a y equals 2x. But do a double check on me. Do those two lines look good? 2x, 1x, we're good to go?
Yeah, looks good.
Okay, so here we go. We're going to do a y equals x to y equals 2x, and an x equals 0 to an x equals 2, and dy then followed by a dx. And I think that one's a pretty much, dot, dot, dot question. We're still good. Green's theorem's doing his thing. We're almost finished, these guys, so that's nice news. Let me pause for a minute. I know I've got a couple of questions, but let me do this as an issue. I'm not going to talk about the whole question, but this thing. Suppose you have a line integral that looks like that, because sometimes the dx is missing, right? Sometimes the dy is missing, right? You don't always get both pieces. I mean, that can happen. If I was doing that question, I have to be careful about who the p and who the q is. Agreed? What is 7x squared? The p or the q?
Q.
Anything that's got the y is the q. And what's p going to have to equal in the context of this question?
0, because there isn't any.
Okay, so when you do your double integral over d, you're going to do this thing with x's, right? Take away this thing with y's, dA. So your double integral is going to be 14x, take away nothing. And so your double integral is going to be 14x. Are you okay with that, right? You could have a dx missing, you could have a dy. That's what you do if it happens, right? So, I mean, Green's theorem is pretty versatile, right? Don't matter if a piece is missing. Green's theorem still works. So far, so good. Let's return now to another one of those ones that we haven't done. Oh, darn it in space. Which one? Yeah, this one. Okay, our last one for today. We'll continue these tomorrow. It's a line integral of e or x e to the negative 4x dx plus an x to the 4 plus 2x squared y squared dy. And the c is the boundary of the region between two circles. So the one we got is this fella. And the other one is this fella. And so if I draw a little picture, basically, don't we just have a circle inside a circle? It's a donut. I'm not sure what they mean by the boundary between them, but it doesn't matter, because don't I know what D looks like, which is more important. Right. So if I'm setting up the region D, would you agree that is a good candidate for polar? And so I would do R goes from 9 because of that radius and 5 because of that radius. And I would do theta from 0 to 2 pi. The guy I'm going to call P is this, and the guy I'm going to call Q is this. So my fella is going to be the double integral over this region D of that guy, take away that guy. So it's going to be an integral from, well, let's just wait a little while to see what this looks like. If you differentiate this with respect to x, you're going to get 4x cubed plus 4x y squared. Take away, if you differentiate this guy with respect to y, you just get a big fat 0. So we're going to have a double integral of 4x cubed plus 4x y squared. I guess I'm rewriting myself here. Okay. I need to turn this into polar, don't I? Right, so I'm going to do an integral from theta equals 0 to theta equals 2 pi. And I'm going to do an integral from r equals 5 to r equals 9. And I'm going to turn this guy x and this guy y into sines and cosines. Okay. And that's going to be a pain in the butt, isn't it?
You suck an X out, so it's a little prettier.
That's right. So why don't I suck a, well, I could sick, yeah, but because I'm turning into polar, it's not going to be of much use to me, unfortunately.
Wouldn't it be
So-
4r squared if you take an X out, and then you'd have the r cos theta?
Oh, then I'd have an x squared plus y squared gets me r squared. Is that what you're thinking? I like your thinking. Okay, I'm pulling out the 4x, and that's going to leave me with that guy. This guy is r squared. That guy's going to be r dr d theta. And 4x, isn't 4x just going to be 4r cos thetas? Okay, so I now have from theta equals 0 to theta equals 2 pi, from r equals 5 to r equals 9. And it's going to be 4r to the 4 cosine theta dr d theta. Check that. 4r and r squared and another r. That's this bit cosine. Okay, that one's good to go. That actually is quite nice, isn't it? Can't you separate them out? And so if you want to do the separation, it's 0 to 2 pi of a cosine function. And then it's going to be from r equals 5 to r equals 9. Oh, darn it in space. I should have seen this coming. What's the integral from 0 to 2 pi of sine theta or cosine theta?
That would be 1 minus 1, which is 0.
So when it would just be
The
0?
exponents would just be a big fat 0 because of the cosine.
And so isn't the whole thing just going to be a big fat 0? So I was making my life a lot harder, although I didn't know it was going to be that easy until, you know, it kind of tidied itself out. Now this line integral is 0. That doesn't mean that this is a conservative field, agreed? Remember, you know, all dogs have 4 legs, but just because you've got 4 legs doesn't make you a dog, right? Right. All conservative fields have a line integral of 0 if they're a closed loop. All line integrals of closed loops. A closed loop of 0 doesn't mean necessarily that you're a conservative field. Said that kind of weirdly, but I know what I was trying to say. Okay, that looks like us for today.